Hello girls, I just wanted to record you a short video to help you work your way through page 12 of your booklet just to make sure that you understand this idea of echoes. So at the minute you should have watched the two introduction videos that I included in the instructions, so make sure that you've watched those. If you haven't watched them, pause this video and check out the links in the instructions so that you have watched those first. But hopefully you're all familiar with this idea of echoes, and you've probably met those in your everyday life. Maybe if you've been in a big sports hall, a big open space where you can hear echoes of your voices. That can be quite frustrating at times when you're maybe trying to play sport and you've got all the sound of people echoing around the room. Or it might have been if you were in a big open space with maybe cliffs or mountains nearby and you can hear yourself echoing from that. And why are echoes produced? Well, echoes are produced when sound is reflected. So if you want to write that in your notes there at the top of page 12, echoes are produced when sound is reflected off a solid object. Now, what we're going to have a look at now is one of the applications which you hopefully saw in the introductory videos, that echoes can be used by ships to find the depth of the sea below them. And what happens is the ships or the boats or even fishing boats will send out a sound signal. So that can be either a sound that we can hear or what we call ultrasound, which would be outside our hearing range above 20,000 hertz. But that signal would still produce a sound wave, albeit we wouldn't be able to hear it. And what would happen is that, so say for example, the sound is produced here. That would travel, and say this was the bottom of the sea, that would travel to the bottom, and when it hit the bottom, it would be reflected, and the sound signal would go back up, and there could be a detector at maybe at the other end of the boat that could pick up the echo. And if we work out the time that it takes for that second sound to be heard, the echo to be detected from the boat, and we know the speed of sound in water or the particular medium that it's in, then we can actually work out the distance between, in this example, the boat and the bottom of the sea. And how we do that is using this equation here that we see on the right hand side. I'm not sure how familiar you are with equation triangles. But you can see that we've got three things that are linked here: distance, speed and time. And from this triangle we can actually get three equations. All you do is you cover the thing that you want to work out. So say for example I want to work out the speed. Let me put a line through that. Okay, what I'm left with is distance and time. But you can see, and if I abbreviate it just to S for speed, distance is over time. So S equals D over T, or speed equals distance over time. If I wanted to work time out, I would cover time. You could even do that with your hand, and you'd be left with time equals distance over speed. So distance divided by speed. And if I want to work out distance, which is what we're doing here, I would then cover distance, and what would I be left with? I'd be left with speed and time, but because they are on the same level, essentially we multiply them by each other. So distance equals speed times by time. And this is the equation that we are going to learn, and I'd like you to write that out. Perhaps in full might be best. This is the one form of the equation that we're going to learn and use. That distance equals speed multiplied by time. Okay, so write that into your notes, put a box around it, put a big star at it. You need to learn that equation off by heart, because if you were asked in an exam to work out the distance from the speed of sound and the time taken for an echo to be detected, then you need to know that equation, distance equals speed multiplied by time. So before we jump into this calculation, I'm going to show you a short animation to just put this in context again before we do the calculation. This is an animation that I would have shown you in class that was on the flip chart, and we would have seen that if we were in school. So I've just recorded it off the computer screen and videoing it on my iPad. So it's not perfect and it's a wee bit shaky, but hopefully it will help you understand the context of these calculations. So if we pause at the end of the animation, you can see, and obviously this is just an animation, but it gives us an idea of what actually happens when fishing boats or ships use this this technique. And it's something called sonar, so it's using echoes in the context of finding out, of navigating and of finding distance. Sonar stands for sound, navigation and ranging, and we'll come back to that in a second. But you can see here, if you were watching that animation, you will have seen the signal being given out by this generator, and then the echo being detected by the detector over here. And what then that will correlate to is the sonar display, and you can see the original sound is at 0, a time of 0, so that's when it initially goes out. And then this is the signal that is detected by the detector. It's the echo essentially. So the first one is the original sound, and the second signal is that echo. And you can see there it was detected 50, and that scale is in milliseconds, so that's actually 0.05 seconds. So the original, at the time between the original and the echo, was 50 milliseconds. And from that, what we could do is find out the distance from the fishing boat to the bottom of the sea, or it can also be used to detect shoals of fish, so groups of fish that are swimming about, and they will also, because they're solid objects, they will also reflect the original sound signal. And so therefore the fishing boat could use that to detect how far down the fish are. So let's go back to the calculation in your notes on page 12. Okay, so it says here, a ship sends out a burst of sound. This is reflected by the bottom of the sea and back to the ship. Suppose it receives the echo 0.6 seconds after the original burst was sent out. The speed of sound in water is 1100 or 1100 metres per second. Calculate the depth of the sea. Okay, so what I want to use is this equation, distance equals speed times time. I want you to write that out again, because we always want to write our calculations out in full. So the distance equals speed times time. So you've been given the speed of sound in water is 1100 metres per second, and you've been given a time of 0.6 seconds, but we need to have a think about the time for a second. Because that is the time taken, and if we go back to our little diagram here, it's the time taken for the sound to go from the boat to the bottom of the sea and back again. But I actually only want to work out the distance between the boat and the bottom of the sea. That's the only distance I want to work out. I don't want to work out then the distance back to the boat again. It says calculate the depth of the sea. So I'm essentially working out what half that total pathway is. So therefore, if it took 0.6 seconds to go from the boat to the bottom of the sea and back again, how long did it take to go from the boat to the bottom of the sea? Well, it will have taken half the time, okay? So 0.6 seconds is the time taken to go from the boat to the bottom of the sea and back again. So therefore, it would have taken 0.3 seconds to get to the bottom of the sea, and then 0.3 seconds to get back to the boat again. Can you see how that works? So it's a total time of 0.6 seconds, but half that time will be taken to go from the boat to the bottom of the sea, and half the time will be taken to go from the bottom of the sea back to the boat again. So in these calculations, you always divide the time by 2. You take half of the time, okay? So I want you maybe to put a wee line out from that if you can, in a different coloured pen if you had it. You always half the time, or if you'd prefer to write it, divide the time by 2. So the time taken for the sound to go from the boat to the bottom of the sea, time equals 0.6 seconds divided by 2, or taking half of it, which equals 0.3 seconds. So we're just using half the time. So then let's complete our calculation. The speed we've been given as 1100 metres per second, and you can see that's in matching units because our time is in seconds and our speed is in metres per second. Now you may be given a slightly different speed of sound in water, or the question could be an air example, maybe by the ship blowing a horn and bouncing off a cliff or a mountain nearby or something like that. So just use the speed of sound that you're given in the question. So don't, if it's a slightly different value, use the one that's in the question. So the speed is 1100 metres per second. The time taken to get to the bottom of the sea is 0.3 seconds. And then just simply put that into your calculator. So you will need your calculator for this. So if you haven't already done so, get that out. Maybe pause the video until you've got that out. If you put that into your calculator, it should work out as 330, but we must make sure to put units at the end of our answer. If the speed of sound is in metres per second and we've multiplied by 0.3 seconds, then our answer is going to be in metres. Okay, so it's whatever the matching unit is for your speed. So you might want to put a note in there, remember your units. Okay. So hopefully that makes sense. Just it's a simple equation, distance equals speed times time. The calculation is not that hard, but what you've got to do is remember that we need to use half the time, not the whole time. And then just put it into our equation, and then remember to put the units at the end. Okay, we'll do a little bit more practice of that in a second, but just to finish off page 12 for now, I'm going to scroll down. As I said earlier, this process is called Sonar. And that stands for sound, navigation and ranging. So the SO comes from sound, the N comes from navigation, A comes from and the R comes from ranging. Sound, navigation and ranging. So it can help boats navigate, can help other vehicles navigate. And it can also help with ranging, in other words, sort of judging distances between things. So for our boats, judging the distance to the bottom of the sea. And also maybe judging distance to a group of fish. Okay, so what I'd like you to do now is pause the video for just a few minutes, and I want you to see if you can answer the following questions based on the videos that you have watched, the introduction video and what we've talked about in this little teaching video. The one thing I would like you to change before you do that is the third question down. It says, does sound travel through different materials at the same point? It should say there at the same speed. Okay, and that's just simply a yes or no answer, and then it asks you how do you know afterwards. Okay, so just change that word point to speed. So pause the video now and have a go at the questions. So make sure you've had a go at the questions yourself before you go through the next part of the video. I'm just going to take you through these questions really quickly to make sure that you've got the correct answers and understand this, okay? So the first question was, why is sonar a valuable safety measure, particularly for boats? Well, really, it's based on that idea of boats being able to gauge the depth of the sea, because obviously boats need a certain depth of water to be able to keep afloat, to be able to keep moving. And if they run into water that is too shallow, then they can what we call run aground, which just means essentially the bottom of the boat would hit the bottom of the water. And if it kind of goes on land, then that can be damaging to the boat, and obviously means it can't travel any further. So it might be like a sandy bank or rocks or whatever that may be. So it gives warning if the water is getting shallower, so you can avoid running aground. And you don't need to have that word for word, but as long as you have something along those lines. Next question was, how would sonar be especially useful to a fishing boat? Well, your answer to that should be something along the lines of sonar can be used to detect a shoal or a group of fish, since they reflect sound. It can also give the fishermen an idea of how far to let their nets down to catch the fish. But that idea, if they are moving in particular, they can send out these signals, and if they get that reflection, then they know that there's fish nearby, because the fish will also reflect the sound. Next question was, does sound travel through different materials at the same speed? So you're thinking, does it travel in the same speed through water as it does through air? And the answer to that is simply no. And how do we know that? Well, if you look back to the previous page that you were looking at earlier today or yesterday, we learned that the speed of sound in air is 330 meters per second. And if you've managed to do your little experiment out in the park, for example, then you may have calculated a value around about that value, depending on the conditions and the different maybe buildings in the area. But we learned that sort of on average the speed of sound in air is 330 meters per second. But here earlier in this page we learned that the speed of sound in water, if you just look up the page a little bit, is roughly 1100 meters per second. And as I said to you earlier, in different questions it might be coded as a slightly different value. It could be coded as, sort of anything up to 1500 meters per second, but we can see there's a big difference between these two values anyway. The speed of sound in air is much slower than it is in water. And we talked a wee bit about this earlier on in the topic, at how sound can travel through gases, liquids and solids. But if you think about the particles in a gas, they're really, really far apart. In a gas, and remember that sound travels by vibrations. It's why sound cannot travel through a vacuum, because it needs particles to pass on the vibrations. So the particles in a gas are really far apart, and so therefore it's slower for those vibrations to be passed along. But then in a liquid, the particles are closer together, and they're maybe not as close as a solid. There's a wee bit of space for them to move past each other. That's why liquids flow. But the particles are much closer together than they are in a gas. So therefore the vibrations of a sound will be able to be passed on much quicker through a liquid than a gas. And that's why the speed of sound travels faster in water than in air. Okay, so your answer to the question, does it travel through different materials at the same speed? No, it doesn't. So lastly in this teaching video, I want to take you through the worksheet that I'd like you to give a go at now. This is in your Microsoft Teams Science page under the Files section in your work for today. But I wanted to take you through the first example. Now, a couple of different options you have for this. Either you can print out this worksheet, there's 2 pages to it, or what you can do is you'll see in your sound booklet that there's a blank page on the next page, the one after page 12, and so therefore if you want to just carry out the calculations on that page, that's absolutely fine. So let's do the worked example together, and what I would advise is that you just listen along now, and then you can write in your answer on the worksheet if you decide to print it out, or just on your blank page in the next page if you don't. Again, make sure you have your calculator out so that you can do these with me, and that there's other examples in the next page that I want you to try for yourself. So let me just zoom in here so you can see this. So it says this worksheet is to help you practice calculations involving echoes and sonar. If we know the speed of sound in air and water, we can calculate distances using the time taken for an echo of a sound wave to be detected. So those are our three key things that we need for our equation: speed, distance and time. Those 3 things are related to each other. And we can calculate the distance using the equation distance equals speed times time. We've met that on the previous page, on page 12, but you must know that equation off by heart. So let's have a look at this first example here. It says here, a boat sends out a burst of sound. This is reflected by the bottom of the sea as an echo. The boat receives the echo sound wave 0.1 seconds. I'm just going to circle that. You might want to highlight that. After the original sound was sent out. The speed of sound in water is 1100 meters per second. Again, and you'll see in the next examples that's sometimes coded as a different value, but always use the value that's been given to you in the question. Calculate the depth of the sea you're asked to do. That's really the distance between the boat and the bottom of the sea. So you may want to write that in, because our equation is going to be distance equals speed times time. So that word depth is just the distance between the boat and the bottom of the sea. Okay, so again, if we look at our diagram here, I'll just annotate this slightly so that you can have a think about what's going on. The boat is sending out the signal. Okay, it's travelling to the bottom of the sea, and then it's being reflected and going back up. Okay, and what we're told is that the total time it takes for it to go to the bottom of the sea and then be detected by the boat again is 0.1 seconds. But remember, I only want to work out the distance between the boat and the bottom of the sea. So what I do with that value of time is I divide it by 2, because it takes a total time of 0.1 seconds to go from the boat to the bottom and back, but I only want half that, and that's written in italics just below. Okay, so remember the time taken is for the sound to travel from the boat to the bottom of the sea and back to the boat, i.e. it has travelled twice the distance we want to calculate. So therefore the first step is to always half the time value, and you're better doing it at this stage before you forget. Okay, so if I write this out in full, the equation I want to be using is distance equals speed times time. But let's think about what my speed is and what my time is and make sure I get those values correct. So the speed is 1100 or 1100 meters per second. The time is not 0.1 seconds, it's 0.1 divided by 2. Put that into your calculator and you'll get 0.05 seconds. Really, really important that you remember to divide that by 2. So there, let's just put that into our equation. So it's 1100 multiplied by 0.05. All you need to do now is put that into your calculator. So do that for me now. And that should work out as 55. But remember, we need units here. If the speed was 1100 meters per second, the time was in seconds, then that value of distance is in meters. If the speed was in kilometers per second, then our distance would be kilometers. But your speed should be given to you in meters per second, or it could be a different unit, but it'll generally be meters per second. So the distance between my boat and the bottom of the sea is 55 meters. So again, just make sure you remember to divide that time by 2 before you do that calculation. And then you need to learn that equation off by heart as well. So that's the first one done. Again, probably best to print this page if you can, because of the notes that are given to you there, or you might want to write out that example in full, write out the question and that little remember note there, and do your first worked example at least out in full so that you have that in your booklet. So do that on the blank page on page 13, well, the page after page 12. I don't know if it has a number on it. And let me just show you the second page so you know what to do now. So the second page says practice questions. There's just 3 more questions, okay? The first one, I've given you the information in bold, but I haven't done that in the second and third question, so you'll have to think, what values do I need to use here, okay? But just remember, you're always going to be dividing the time by 2 and using that equation, distance equals speed times time. And can I just ask you, as you're practicing these, to always write the equation out and write your working out in full. And then remember to put your units in your answer. Because if you don't write your working out, then you can't get any marks if your answer is wrong. Whereas if you've got your working out, you might get some of the marks in a question. And these questions tend to be worth 3 marks. Maybe 1 for the equation, 1 for the final answer, and 1 for your units. So make sure you write it out in full, as we have been doing already. The first question is about a ship, and you're asked to do the depth of the ocean, just what we've been doing. Second question is about a car, and it's about the speed of sound in air, but the concept of the calculation is absolutely identical. It's just the car detecting an echo of the horn being sounded, but you're using the speed of sound in air. Always just use the speed that you've been given and the time that you've been given. Okay, so have a go at those 3 practice questions, and then we'll go through your answers next week.